Hi there! In Houdini, you are just one click away from getting a decent visual effect. In the shelf dock, you can find many useful presets to get started with this task. And when using a preset, Houdini will lay out all the networks and nodes to achieve the required result. Let's start building networks using the shelf tools. Let's create a smoke. Go to the Pyro FX tab, click on the Billowy Smoke tool. A message is displayed. Select the source of the Billowy Smoke. The source must be an object. So we need to create an object first. Press Escape. Now in the Create tab, hold Ctrl and click on the Sphere tool. A sphere object is created and is selected. Try again the Billowy Smoke tool. Okay, the sphere was converted into a cloudy shape, and in the network editor we are inside a node named Auto Network. This is not a geometry network, but a dynamic or DOP network. You can see the word dynamics in the network editor. Later we will return to this network. Click on OBJ to go to the object level. Before using the Billowy Smoke tool, we only had the Sphere Object 1 node, which is a geometry network. Now we have two additional networks. A dynamic network named Auto Network. This network contains all the nodes to perform the dynamic simulation. But simulation data is only data and cannot be rendered. That's why Houdini sets off the display flag on this node. To render the simulation data, Houdini creates a geometry network named Pyro Import. The display flag on this node is set to visible. Inside this node, the simulation data from the Auto network is imported in this geometry network so that you can render it. In regards to the Sphere Object 1 node, this was used as an emitter for the smoke. As needed, you could let its display flag as visible or hidden. It's quite important to understand this workflow, as this is practically used in all types of simulations: rigid bodies, soft bodies, pyro, fluids, particles, etc. So let's recap this workflow in a slightly different way. First, you have a source geometry network. Inside, of course, you have geometry nodes. Sometimes this data can be used as it is in the DOP network, but most of the time a few extra nodes are needed to set up the data for the simulation. Second, in the dynamic or DOP network, the data from the source geometry network is imported and used in the calculations for the simulation, and all the calculations are always stored in a node inside the DOP network. Third, in the output geometry network, the data from the DOP network is imported so that you can render it. Sometimes extra nodes are added to post-process the simulation data. Okay, that's an overview of how simulations work in Houdini. Let's continue. To better view the smoke, let's change the background color. Press D to open the display options. Go to the Background tab and change the color to dark. Close the display options. Also turn off the reference plane. Play the simulation. Okay, that's the default result. Not bad. Note that in the timeline, a blue line shows the simulation frames that have been cached on your computer. In the timeline, change the end frame to 96. Play the simulation. Activate the real-time toggle to have a better sense of the speed. Play the simulation. To see more detail in the smoke, let's add a light. Lights work in a similar way like cameras. Go to the Light tab and Ctrl-click on the Area Light. An Area Light 1 node has been created and is shown in the Lights and Cameras menu. Click on the Lock tool. Now you can move the viewport and the position of the light will be updated. Okay, click again on the Lock tool to unlock the light from the viewport. Now you can move the view, but the light will remain in its position. Go to the last frame and move the view to frame the smoke in the viewport. Let's review the DOP network in more detail. Double-click to dive inside and maximize the pane. Dynamic networks and in general node networks are always perceived to be the more difficult part to understand in Houdini. However, this is only a misconception. In the last episode, we already created our first node network without too much problem. Besides, in our daily life we deal with more complex processes and challenges, but most of the time we take action and solve the problems almost without being aware of every step we take. Let's recall the simple process we analyzed in episode 02 of this section, creating an omelette. We have the ingredients and the process. And if we represent this recipe as a node network, we have this graphic. For the ingredients, in the parameters tab, you would expect the amount as a parameter to control. In the heat on pan node, you would expect to control the temperature and heating time. For the mixing bowl node, the mixing time. For the cook node, also the temperature and cooking time, and so on for the other nodes. And finally, you get the omelette ready. Now, if we go back to our Pyro network, we can see it's rather simple in comparison with making an omelette. Of course, the Pyro nodes have many more parameters to manage, but the general process is pretty similar. Here, we also have ingredients. The first ingredient is a Pyro node, which is a smoke object. And, by the way, this is the node that holds the simulation data. The second ingredient has a long name, Source Density from Sphere Object 1, and it is a volume source node. From the name you can guess, this node brings or imports the data from our source geometry object. And the main process is executed by a node named PyroSolver1. We have two additional nodes. The resize container node to control the simulation boundaries, and the gravity1 node to apply a gravity force to the simulation. Okay, let's change the main parameter of the simulation, the resolution. This can be found in the Pyro node, and it's called division size. The smaller the parameter, the greater the resolution, but also the greater the required RAM and simulation time. Change it to 0.04. Restore the network editor pane. As we changed a parameter, we lost our cached blue line. Now we have an orange line, so we need to play the simulation again. Return to the first frame. When you increase your resolution, at some point you won't be able to play the simulation in real time. To solve this issue, you can make a playblast or a flipbook. Press the flipbook tool. The render flipbook window opens. The main parameter to change here is the frame range. Change it to 1 to 96 and press start. The endplay window opens. Let the process end. Okay. Now we can play the simulation in real time. Even with the default parameters, we have a decent result. Nice! Let's move on with another visual effect. Close the flipbook. Reload current desktop and create a new scene, discarding the changes. Let's now use the Fireworks preset. Go to the Particles tab and press the Fireworks tool. This preset does not require an object, just a location to emit from. Press Enter to set the location at the center of the scene. As in the first example, we end up inside an Autodoc network. Press on OBJ to go up one level. Play the simulation. It plays too fast. Activate the real-time toggle option. Play the simulation. Let's change the background to black. Press D to show the display options. Go to the Background tab and select Dark. Play the simulation. Okay, it looks better. The workflow is the same, Although in this case we don't have an explicit source object, but we have a position to emit from. In the Autodop network, the source position is used to emit particles. Then in the Fireworks Particles node, the simulation data from the Autodop network is imported to be rendered. Dive inside the Autodop network. Press L to arrange the layout. Here you also have the ingredients and the solver. Go to the object level. Now dive inside the Fireworks Particles node. Here you can see the Import Fireworks node. This node, as indicated before, imports the simulation data from the Autodop network. Go to the object level and play the simulation. Okay, quite easy, right? Let's move on with another visual effect. Reload current desktop and create a new scene, discarding the changes. Let's now make a rigid body simulation. We are going to create a bunch of balls and make them fall to the ground. Control-click on the sphere tool to create a sphere at the center of the scene. Change the primitive type to polygon, increase the frequency to 3, and the size to 5. Create another sphere. Control-click on the sphere tool. We can't see it. Hide the first sphere. Now we can see the small sphere. Activate the display flag on the first sphere. Now on the Modify tab, press on the Copy to Points tool. Select the geometry to copy. In this case, select the small sphere. Press Enter. Now select the geometry on whose points to copy the data. In this case, select the big sphere. Press Enter. OK, the small sphere was copied onto the big sphere points. If you check the network editor, you would probably say it would have been easier to do it from scratch, creating both spheres inside the network editor and connecting them with the Copy to Points node. And yeah, you would be right. Anyway, we have the required bunch of balls. Go to the object level, move the balls in the Y direction. Rename the object as balls. Now go to the Collision tab and press on the Ground Plane tool. Two nodes have been added: the Autodop network to execute the simulation, and a Ground Plane Object 1 node to represent the ground to be used as a collision plane in the Autodop network. At the moment, only the ground plane is considered in the simulation. We also need to set our bunch of balls as rigid body objects. So select the balls and go to the Rigid Body tab. As we don't want all the objects behave as one single rigid body object, select the RBD Fractured Object tool. A window opens asking you what type of fractured object. Select the RBD Packed Object option. Fingers crossed and play the simulation. Okay, not bad, but it would be better if we can get bouncy balls. By the way, in regards to the workflow, the source geometry in the balls node and the ground plane node are imported in the Autodop network, and then the simulation is executed in this dynamic network. Here we don't have an additional node to import the simulation data. Instead, the simulation data is imported back inside the balls node. Dive inside the Autodop network and press L to arrange the layout. Again, here we have the ingredients and the solver. In this case, the first ingredient is the ground plane, which has some physical properties. Increase the bounce parameter from 0.5 to 0.8. The second ingredient is the RBD packed object named balls. Also change in the physical properties the bounce parameter from 0.5 to 0.8. Okay. Now, the gravity node is a force that acts on the simulated objects. Change it from minus 9.8 to minus 3.8. Play the simulation. It's better. Let's do a flipbook. Press the flipbook tool. Leave the default parameters and press Start. Let the process end. Play the flipbook. Nice! You have successfully made a basic rigid body simulation. Let's move on with another visual effect. Close the flipbook. Reload current desktop. And create a new scene discarding the changes. Let's now make a sub-body simulation using the Vellum tools. We are going to try it on a squab test geometry. On the viewport, press Tab, and in the Test Geometry category, select Squab. Press Enter to place it at the center of the scene. Move the squab up. In the timeline, change the end frame to 120. In the network editor, rename the object as Squab. Select the squab and go to the Vellum tab. Press on the Vellum Strut Subbody tool. As usual, we end up inside an Autodoc network with two ingredients, a Vellum object and a squab Vellum source. And also, as usual, we have a solver. In this case, is a Vellum solver. Go to the object level. Once again, the same workflow. We have a source object with the display flag off. This geometry is preprocessed in this node. Then we have the Autodoc network, in which the data from the squab node is imported and simulated. And finally, a sub-body Vellum node in which the simulation data is imported to be rendered. Before starting the simulation, add a ground plane to collide with. Go to the Collision tab and press on the ground plane tool. A ground plane object is added as a geometry at the object level, but also as a collider in the Autodoc network. Play the simulation. And it works. With the default parameters, we have a decent result. Let's do a flipbook. Press the flipbook tool. Change the frame range to 1 to 72 and press Start. Let the process end. Play the flipbook. Okay, it looks fine. Let's move on with the last visual effect. Close the flipbook, reload current desktop, and create a new scene, discarding the changes. Let's now make a terrain valley. Terrain tools are rather geometry setups, but they can also provide simulation tools to erode the terrains. Just to check, restore the hidden left pane. In the Terrain tab, press on the Terrain Valley tool. A terrain is created and we end up inside a geometry node named Terrain Valley. Go to the object level. In the tree view, you can check the created nodes. Dive inside the Terrain Valley node. Now, close the tree view. We don't need it anymore. Let's explore the nodes in the network editor. The first one is a hayfield node. It is just a grid with size and resolution. At the moment, the size is 1000 by 1000 units, and the grid spacing is 2 units. The second one is a noise node. This node defines the main shape of the terrain. The main important parameters here are the amplitude, at the moment set to 500. This defines the height of the noise. The element size, at the moment set to 600. This defines the size of the noise. And the most important, the noise type, at the moment set to Worldly F1. The third one is a Distort by Noise node. This node adds a small detail to the terrain. The main important parameters here are also the noise type, the amplitude, and the element size. And the last one is an Erode node. This node simulates an erosion process on the terrain. There are a lot of parameters to play with. Just leave the default values. Play the simulation for a few frames. Okay, you can see what this node does. Go to the first frame. Go back to the hayfield node. Change the size to 1500. And to have more detail, decrease the grid spacing from 2 to 1. Now select the noise node. You can use the offset parameter to change the position of the noise. Change the amplitude to see the effect. Also change the element size. Play the simulation again. Go back to the first frame. Now select the noise node. Let's try another noise type. Select sparse convolution and tweak the amplitude and the element size parameters at your taste. Play the simulation. Okay, that looks interesting. With a basic terrain network and almost with the default parameters, we have managed to get an interesting terrain. Well, that concludes this video. We have made a quick exploration of some common visual effects in Houdini. To learn more, continue exploring the shelf dock presets by yourself, analyzing the nodes and networks Houdini creates, changing parameters and watching the results. Thank you for watching this video. I'll see you soon in the next one.